Look at worksheet number 20 here, starting with question number 6. It says the work function of a particular metal is 2.50 EVs, or electron volts. Will visible light of wavelength 5.50 times 10 to the, that should have been 10 to the negative 7. I think I mentioned that to you yesterday in class, didn't I? 5.50 times 10 to the negative 7 meters. Would that cause electrons to be ejected? Photoelectrons, right? Photoelectrons are just electrons that have been ejected. So would we get photoelectrons here? Would electrons be ejected here? There's two ways that you can do this, just like question number 5. There's two ways you can do it. The first way is to find the threshold wavelength. We know that the work function is h times the threshold frequency. We also know that it's hc over the threshold wavelength. Threshold wavelength being the max wavelength. Let's solve for that. Let's solve for lambda max here. That works out to be hc over w, and when you solve for lambda max, it gives you 4.968 times 10 to the minus 7 meters. Now, if you want electrons to be ejected, you want your wavelength to be not above, but below your threshold wavelength. You want it to be above the threshold frequency or below the threshold wavelength. Is the wavelength of this light here, 5.50 times 10 to the minus 7, is that below the threshold value of 4.96 times 10 to the minus 7? It's not, right? The wavelength of the light is bigger than the threshold wavelength. The wavelength needs to be smaller than the threshold wavelength. That means that no, electrons will not be ejected because our wavelength is too big. Our wavelength is bigger than the threshold wavelength. Now, the other way to do this is to have calculated the energy of that photon, hc over lambda. The energy of this photon right here using 5.5 times 10 to the minus 7. Now, I don't have the answer here because I didn't calculate it this way, but if you calculated that in electron volts with the 4.14 value of Planck's constant, then you're going to get a certain value for the energy of that photon. In order to cause the electrons to be ejected, you would want your energy to be bigger than the work function. Wavelength smaller than the minimum, or sorry, than the max wavelength, but you would want your energy to be bigger than the work function. And you would find that in this case, it's not. So once again, you'd find that no, electrons would not be ejected there. Next one we want to go over is number 10. It says calculate the minimum speed of a photoelectron emitted from a metal whose work function is 2 electron volts if we illuminate the metal with light of frequency 2.5 times 10 to the 15 hertz. So we're ejecting electrons here. The photoelectric effect has happened. We want to find how fast the electron could be moving here. Let's write down some givens here. We have a work function of 2.00 EVs. We have a frequency of EMR of 2.50 times 10 to the 15. This is not the threshold frequency. This is not F0. This is not the frequency at which electrons begin to be ejected. We're just saying, look, this is the light we have. Maybe it's just a little bit above the threshold. Maybe it's way above the threshold. I don't know. This is just the light we have. It's the frequency, not F0. We want to find Vmax. Remember the 5-second rule? Not the one that says when you drop food on the floor, can you eat it? If you pick it up within 4 seconds, you can eat it. Okay, not that 5-second rule. But the 5-second rule that says if you can't figure out what equation to use in the photoelectric effect within about 5 seconds, what should you do? Yeah. 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 Remember that one that we had in red yesterday? Go to the red one. HF is equal to EK max plus W, as Cody said. Now, we have F and EK max. What are we going to do with EK max? These ones are fine, but EK max isn't going to work out for me. EK max is equal to, yeah, 1F MV max squared, plus W, of course. Now, we've got our work function in electron volts, right? Could we, if we wanted to, convert it to joules? Sure we could. We can always use joules, right? Do we have to convert it to joules? Do we need to, or could we use electron volts? Hannah? Yeah. Good, good. If we were using this we'd be fine either units. But as soon as we introduce QV or 1 half mv squared, we've got to use joules now. So let's convert that 2 electron volts to joules. We know that 1 EV is 1.6 times 10 to the minus 19 joules. 2 EV is x joules. So x works out to be 3.2 times 10 to the minus 19 joules. All right, let's sub in our numbers here. 6.63 times 10 to the minus 34 joules seconds times 2.5 times 10 to the 15. We always use the mass of an electron here because that's what's ejected. And the work function is now 3.2 times 10 to the minus 19 joules because we want it in joules. So what you want to do here is calculate this number and then take this number over by subtracting because it's added to the rest of it. And then multiply by 2, divide by 9.11, and then square root it. And when you do that, for number 10, it works out to be 1.71 times 10 to the 6. You guys okay with the algebra there? Do we need to go over the algebra in more detail? Or are you okay with that? And number 12. 12 says when 230 nanometer light, that's the wavelength, right? That's not the threshold wavelength. That's just the wavelength. That's just the type of light that we're shining upon this. Hey, maybe that's above the threshold wavelength. Maybe it's below. Maybe it's way above. I don't know, whatever. When we do this, the current through the photoelectric circuit is brought to 0 at a reverse voltage of 1.64. Do you guys remember the picture that I showed you yesterday? Remember when we reversed this so that we had a negative terminal here and a positive terminal here? That would make this terminal negative and this terminal positive. You remember when those electrons were ejected? Okay, these electrons would be repelled by this negative terminal over here. And if we applied a big enough potential difference, then we could stop those electrons. How did we know when the electrons were stopped? Remember, we couldn't see them, right? We can't just physically look in there with our eyes and see electrons moving or stopping. Cody, how do we know that they were stopped? Good. The current reading going through the ammeter would be 0 if the electrons were stopped. So let's go back to this question again, number 12. It says the current through the circuit is brought to 0 at this voltage. In other words, at this voltage, this potential difference, we're stopping the electrons dead in their tracks. In other words, that is the stopping potential. Does that make sense? When your current is 0, you have no electrons flowing. And when you have no electrons flowing, you must have reached the stopping potential. So V stop is 1.64 volts. We want to find the work function. 5 seconds. 1, 2, 3. Anybody? 4, 5. Okay. Let's try this one then. Nobody came up with something better in 5 seconds. Let's replace HF with HC over lambda. Let's replace EK with QV stop. And then we're looking for W here. Jessica, can we use joules for this? Are we allowed to use joules for this? If we want to use joules, could we? Yep. We can always use joules. Always. Like the answer to that question is always yes. Now, somebody else, do we have to use joules? Yeah, we do. We got to use joules for this one because 1 FMV squared or QV stop, we got to use joules. If we just stuck with this, then we could have used electron volts. But as soon as you replace EK with 1 FMV squared or QV stop, you've got to use joules. Okay, so we sub in our numbers here using joules. 6.63, 3 times 10 to the 8 divided by 230 times 10 to the minus 9. Okay, sub in your numbers there. Take this over to the other side by subtracting once you have your variables in there. Solve for the work function. We're going to get a work function here in joules because we used joules. You get 6.02 times 10 to the minus 19. Now, if the question had have asked for the answer in electron volts, you still would have had to use joules because we use that equation, 1 FmV squared, or QV stop, I should say. But if you had have gotten joules and you needed electron volts, you had to do the conversion at the end. That's all. Q is the charge of an electron, right? Because when we're talking about a charge or a mass, either one within the photoelectric effect, there's only one thing that has the charge and mass, and that thing is the electron. Yeah, V stop will always be volts. Yeah. So remember, EV, electron volts, is energy. Like you could get energy in electron volts or work function in electron volts, but V, potential difference, will always just be volts. Okay, you don't have to worry about electron volts or joules there because it's always going to be volts. Question there, guys? Nope. All right, and the last question we have to do here is number 14. It says, in a photoelectric experiment, it is observed that no current flows unless the wavelength is less than 570. What do you think they're giving me right there? Nothing's going to happen unless the wavelength is less than 570. Yeah, that's not just lambda. That's lambda max. You've got to be below that. That's the maximum possible wavelength. Now, this is actually a pretty straightforward question. If you catch what Kobe got there, and that is that lambda max is 570. Now we're just going to say W is equal to HC over lambda max. Now you can do Planck's constant in whatever units you want. Joules seconds or electron volt seconds, doesn't matter. Whatever you do it in, though, is what you get your answer in. If you do it in joules seconds, you're going to get joules. If you do it in electron volt seconds, you're going to get electron volts. I did number 14 in, what did I do it in here? I did it in both, actually. If you do it in joules, you get 3.49 times 10 to the negative 19. And if you do it in electron volts, you get 2.18 EVs. The answer for 12 was 6.02 times 10 to the negative 19.